Okay, we're trying to use a graph, a force versus time graph, to determine what the impulse is that's applied to the ball as the bat strikes it. So first of all, when we look at the graph, notice that there's no contact, there's no force until it reaches this point right here, which is at 3. But be careful of the units, it's actually milliseconds. So at 3 milliseconds, the ball and the bat first make contact, and then as the ball and the bat squeeze together, they reach some maximum force. You can imagine the ball is all deformed and the bat slightly deformed as well. And then the ball begins to get released from the bat, and the reverse happens. And finally it leaves the bat here at, looks like 7 milliseconds. So the time of contact looks like it's between 7 milliseconds and 3 milliseconds. So 4 milliseconds. The trick is, how do we estimate what this average force is? We know that impulse is average force times time. We can figure out the time of contact. How do we estimate the average force from a crazy looking shape like that? It's certainly not 80. 80 newtons is the maximum force. We're trying to find the average. So what I do, and it's an estimate no matter how you do it, is I estimate a rectangle that will have the same area roughly as the original sort of bell curve shape, that shaded region that's under the graph. So I put a couple of dotted lines on either side, right where it starts and ends. And the idea is I'm trying to create a rectangle so that it has roughly the same area as this shaded region. So all I'm doing is capping off my rectangle so that it looks like the area below my rectangle has the same area as that shaded. Now if I cap off my rectangle right there, you can see that that rectangle area, the one I'm sort of highlighting here with my mouse, is actually a lot bigger. How do I know that? I imagine it like a puzzle. If I split the little piece of the peak here that's above my rectangle and divide it in two, that little half a piece should fit nicely in this side, and this other little half a piece should fit nicely in that side if it's the same area. So obviously I've overshot. So you just kind of eyeball it until it looks like the puzzle fits together. So if I drop this down to about 40 newtons, and then I take this piece here at the peak and I just imagine it split down the middle, it does kind of look like that piece there fits nicely in here, so that'll go down, and that piece there will fit nicely in there. Maybe a little less than 40, but it's pretty close. So the area of my rectangle that's in question here, and I'm just going to erase the bit so we can see what I'm talking about, looks like this, and I'll just shade it. This area here that I've estimated with my rectangle, I'm saying has the same area as that original shaded one. And once I'm sort of happy with my estimate, wherever I capped it off, that's my average force. So it looks like here my average force is about 40 because my rectangle looks about to have the same area. So now you just finish the question. Average force is 40 newtons. The time of contact goes from 3 to 7 milliseconds, so that's 4 milliseconds. Now we're going to have to convert that. Has to be seconds to get the correct units for impulse. So 4 milliseconds, when I convert, there are 1,000 milliseconds in 1 second. So I want to get rid of the milliseconds and get seconds. There's 1,000 of those in one of those. They're going to cancel. So when I go 4 divided by 1,000, I get 0.004. So 40 newtons times 0.004 seconds will give me an impulse of 0.16 newton seconds. And again, that's just an estimate, but it's a fairly close one, I would guess.